This is a video for group work day number 2, exam 1 review. The first question asks us for the product when we treat the following molecule with hydrogen and palladium. We know that hydrogen reduces pi bonds, both carbon-carbon pi bonds and carbon-oxygen pi bonds, so the answer to our question is cyclohexanol. When we treat cyclohexanol with concentrated sulfuric acid and heat, we want to think of an E1 reaction. And you're considering, do you form a pi bond here or here? And the answer is it doesn't matter, because the product, whether you drew it to the left or the right by taking one of these beta protons, is going to be the same. In the next question, we're asked to convert an alcohol into an ether. How do we know how to do that? Well, we know that we're going to use sodium hydride as the base because we need to form this alkoxide, and that needs to attack an alkyl halide and have a leaving group depart. So our reagent is going to be something with a leaving group, so let's say bromine, and then we want to count the number of carbons and acknowledge their arrangement to the new bond. So we have 4 carbons there, and 4 carbons in that reagent. And one thing that I noticed in a lot of student answers is that people tended to leave out this carbon that's highlighted in blue, but you have to remember to count all of your carbons so that you don't leave any out. In the next reaction, where we have the reaction with excess hydrogen iodide, then we need to consider the number of carbons, and what we're doing is breaking these carbon-oxygen bonds and putting an iodine atom on either side of them. So that gives us propanol and isobutanol. With the epoxide ring opening, we're presented with sodium cyanide and an epoxide that has a primary and a tertiary carbon. Because the conditions are basic, we want to attack the less substituted carbon atom. So that was this one. It undergoes inversion, but it doesn't matter what its stereochemistry is because it is not a stereocenter. In our second step with water, we protonate that alkoxide that's formed. Gives us this product. In the case of hydrobromic acid and the same compound, the first thing we want to do is pick up a proton from HBr and form this protonated intermediate. Then we want to think about where the bromine is going to attack. And here we've got a primary versus a tertiary carbon. And in acidic conditions, we want to attack the tertiary carbon. Now we get an inversion of stereochemistry at that carbon. So we want to draw these groups pointed up and the bromine down. In spectroscopy, we're supposed to determine the structure of a molecule with formula C8H10O using the information provided below. The first thing I do when I look at a problem like this is predict the degrees of unsaturation or hydrogen deficiency index. They're the same thing. The degrees of unsaturation for this compound are 4, which for a molecule of this size makes me think automatically a benzene ring. That's consistent with the IR spectra. We have sp2CH bonds and sp3CH bonds in our IR spectrum, which is consistent with a benzene ring. The NMR is really the telltale here. We have protons that are in the aromatic region, and they're in a 2-to-2 ratio. And what that tells us is that we're going to have substituents at the 1 and the 4 positions, so that we have two types of protons that give us these two signals. Now what we've got left are this integration of 3 and integration of 3, and they're a singlet. And what you should see from the following reaction, the conditions, is that we had something that's going to have an OH that is deprotonated with a base to make an alkoxide, and then treatment with CH3Br gives us an ether. So that's going to have to be part of the molecule, so I'm going to go ahead and put an ether at one end, and that's giving us this peak, which is more downfield. Then we've got a singlet that's at about 2.3 ppm, and it's also not split at all, so that's going to have to be a methyl group on the other side, para to the methoxy group, and that is our answer. The next question is to determine the major product for the following transformation. After our first step, what we get is an oxidation reaction. Be careful that you're using the right terminology. This is oxidation when we're introducing oxygen atoms. And then we are treating the product with potassium or pyridinium chlorochromate and DCM. And here what we need is to have a proton attached to a carbon with an alcohol in order to oxidize that carbon atom to become a ketone. The second carbon doesn't have a hydrogen attached to that carbon containing the OH group, so it can't be oxidized. It stays as the alcohol. So that gives us our correct answer is D. The last question could be kind of tricky. It took me a while to get it myself, to be honest. But once you see it, then the answer becomes easier. You're looking for a source of carbon atoms. You have to have a source of carbon atoms, so you're looking to think about reagents like Grignard reagents. How could you incorporate a Grignard reagent and get an alcohol at this third position? The way we're going to go about this is to introduce an epoxide and then have that be attacked by a Grignard reagent. So this carbon is this carbon. And then in our next step, we protonate with water to get to our alcohol. Now, off to the side, I'm going to draw another reaction sequence that works. And this was suggested by a student in group workday. So this student proposed to do an ozonolysis, and then what she wants to do is add 2 carbons here through a Grignard reaction. So this ethyl group is what has added here. And then with protonation, you get back to that alcohol product. That's all for this video. Happy studying.